Today's wireless is fast, but compared with fiber optic cables, it still feels like a dirt road next to a 10-lane highway. Fiber can push hundreds of terabits per second, while our best wireless links are still struggling just to keep up. So here's the hook. A new experiment just showed an all-plasmonic sub-terahertz wireless link that sends 120 gigabits per second on a 285 gigahertz carrier across 5 meters of free space. And it does this without the usual bulky, power-hungry terahertz electronics. Instead, it uses light itself and tiny plasmonic chips as the engine. Let's unpack what that means in normal language first. Then we'll dive into the science. Imagine you have a super-fast fiber optic line racing out of a data center. It hits a physical obstacle, a river, a road, a factory floor, where laying new fiber is a nightmare. Ideally, you just jump that gap wirelessly without slowing down. That's exactly the problem this work targets. The researchers built a link that takes data from fiber, converts it into a sub-terahertz wireless beam, fires it across the gap, and then converts it straight back into light on the other side. The magic trick is how they do those conversions. On the transmitter side, they use a plasmonic graphene photodetector. You start with an optical data signal at 1550 nanometers, like in normal telecom. Then you add a second laser acting as a local oscillator. When both lasers hit the plasmonic photodetector, the detector feels the beat frequency between them as an electrical signal. They choose that beat to be 285 gigahertz. That's in the sub-terahertz band, far above 5G, even above most 6G concepts. Now, this isn't just any photodetector. It's built as a metamaterial perfect absorber with a metal insulator metal stack and a bilayer graphene sheet. Plasmonic resonators on top trap and enhance the light field right where the graphene sits. When the graphene absorbs the light, it generates carriers, and built-in electric fields push those carriers to contacts, creating a photocurrent. Because of the plasmonic design, this photocurrent doesn't roll off at high frequencies the way normal devices do. In measurements, the detector shows a flat frequency response all the way up to at least 330 gigahertz, and the architecture has been shown to work beyond 500 gigahertz. It also runs at zero bias, which helps with power and noise. So out of this tiny chip, less than 50 square micrometers, comes a sub-terahertz electrical signal at 285 gigahertz carrying your data. That signal goes through amplifiers, into a horn antenna and a lens, and shoots through the air across 5 meters. On the receiver side, there's a different plasmonic device, a plasmonic Mach-Zehnder modulator. Think of it as a super small, super fast voltage-controlled mirror for light. It has 2 ultra-short plasmonic phase shifters with a narrow metal slot filled with an organic Pockels material. When the 285 gigahertz signal arrives, it drives the electrodes around that slot. The electric field changes the refractive index of the nonlinear material via the Pockels effect, which shifts the phase of light passing through the slot. Because the slot is only about 120 nanometers wide and a few micrometers long, the overlap between optical and RF fields is huge. The device behaves like a tiny capacitor with a bandwidth measured to be flat up to around 350 gigahertz and designed for almost 800 gigahertz operation. They bias the modulator at its null point. That means a small voltage swing from the sub-terahertz signal translates into strong modulation of the optical output. The result is that the incoming 285 gigahertz waveform gets imprinted onto a new optical carrier as a pair of sidebands. Those optical sidebands go into a standard dual polarization coherent receiver, where more familiar digital signal processing takes over. Timing recovery, matched filtering, equalization, carrier recovery, and combining the 2 sidebands to get a few extra decibels of signal-to-noise ratio. So what did they actually send? They used digital Nyquist frequency division multiplexing to carve the signal into 6 sub-bands, or tributaries. Each one carries symbols at 8 gigabaud, for a total of 48 gigabaud. Depending on how strong each tributary looks after it passes through the link's frequency response, they assign different QAM orders and adjust power. This is called bit loading. Put together, that gives a line rate of 120 gigabits per second. After you account for coding and error correction, the net information rate is around 112 gigabits per second, with bit error rates below standard FEC thresholds. Right now, the overall link bandwidth is limited by the RF amplifiers to roughly 30 gigahertz. The plasmonic PD and modulator themselves can go much higher. If future versions of the graphene detector produce more power, you can shrink the amplifier chain or remove it completely and scale the data rate further. Why is this such a big deal? First, it shows that plasmonic devices are not just lab curiosities. They can anchor a real end-to-end sub-terahertz wireless link that rivals fiber speeds over short distances. Second, the devices are tiny, integrable, and energy efficient. They play nicely with silicon photonics and could, in principle, be manufactured at scale. That's very different from today's large, expensive terahertz front ends built from specialized IV electronics. Third, the architecture is naturally optical friendly. Since you start with light, convert to sub-terahertz, then go back to light, you can imagine wireless fiber bridges all over the network, between buildings, across streets, even between racks in a data center. For non-science viewers, the takeaway is simple. This is a glimpse of how future 6G and beyond networks might cheat the laws of convenience, keeping fiber's speed while gaining wireless flexibility. For the science and engineering side of our audience, it's a powerful demonstration of what happens when you combine graphene plasmonics, organic Pockels materials, and silicon photonics in one system. You get terahertz-class bandwidth, linear behavior, and realistic device footprints. So where could this go next? Think short-range, ultra-high-capacity backhaul between small cells. Think high-speed links between buildings where digging for fiber is too expensive. Think data center interconnects that jump fiber gaps wirelessly while staying above 100 gigabits per second. Plasmonic technology still has challenges, improving graphene quality, boosting output power, packaging for the real world. But this experiment shows that an all-plasmonic sub-terahertz link is not science fiction anymore. It's a working prototype. If you want more deep dives like this into wild new hardware for 6G, quantum tech, and next-gen photonics, hit subscribe, ring the bell, and drop a comment. Where do you think all-plasmonic links will show up first? On cell towers, in data centers, or somewhere totally unexpected? Check out more at newswade.com.